Okay, now we have to handle our last situation where we have two complex conjugate solutions. Again, my auxiliary equation is in the form ar squared plus br plus c equals 0, and it comes from the homogeneous differential equation ay double prime plus by prime plus cy equals 0. So again, my solutions are in the form of e to the r1t and er2t. So what does that mean for complex solutions? Let's say my r is equal to alpha plus or minus beta I, where alpha is the real portion and beta is the imaginary portion. So that means my solution, if I model this after what I did with two real solutions, would be c1 e to the alpha plus beta I, all multiplied by t, plus c2 e to the alpha minus beta I, all multiplied by t. If I remember my exponent rules, I can rewrite it like this. And then finally I see I can pull out or factor out that e to the alpha t. So what am I going to do with this imaginary portion? Well, let's just look at this e to the I beta t for a moment. So what we're going to do to solve this is go back to Calc 2 and recall the Maclaurin series for e to the x. Remember, the Maclaurin series is simply the Taylor series centered at 0. This is what the Maclaurin series expansion for e to the x is. So instead of x, we have, let's call this e to the theta. Actually, we're going to call it e to the I theta. So we're going to go ahead and expand out the Maclaurin series for the first couple of terms. So here's the expansion for the first couple of terms. You don't really need to write this down because this is going to come up with a solution that we can always follow, but I do want you to see how it comes to play. So if I look at this, and if I also remember that these are the Maclaurin series for cosine and sine, and if we also remember that things like I squared is simply equal to -1, and I to the fourth, well, that's just equal to +1. I to the third is -I. So if we start looking at this, we start seeing the series adding up for cosine and the series adding up for sine, except with the sine we have an extra I out front. So in other words, e to the I theta is simply cosine theta plus I sine theta. This is also known as Euler's formula. So we can rewrite one of our solutions as e to the alpha t e to the I beta t as e to the alpha t times the quantity cosine beta t plus I sine beta t. And the general solution could be written in this form. The trouble is, we don't really like dealing with imaginary numbers in our solutions. So here we're going to get help from a lemma. If z of t equals u of t plus iv of t, and if that equation solves our differential equation ay double prime plus by prime plus cy equals 0, then u and t are also solutions. They are in fact our real valued solutions. So we now have all three situations. Our two real solutions, our one repeated real, and now our two complex solutions. Those two complex solutions will always be written in the form c1 e to the alpha t, where again alpha is the real portion, times cosine of beta t, where beta is the imaginary portion, not the I itself, but the coefficient in front of the I, plus c2 e to the alpha t sine beta t. Again, with the two real, we'd have r1 and r2. With the one repeated real, we'd have r. And with the two complex solutions, we have r equals alpha plus or minus beta I, but all we care about is the alpha and the value beta. Don't worry about the plus or minus. Let's look at a quick example. This example is a mass that's bouncing up and down on a spring. This is the equation that governs it. M is the mass, B is the dampening coefficient of whatever the medium is that the mass is bouncing in, and K is the spring constant. Let's give some real numbers. These are my values I'm going to use for M, B, and K, and these are also my initial values for my original position and my initial velocity. And let's go ahead and solve this. There's my differential equation. Now I'm going to come up with the auxiliary equation. Next, I'm going to assume that you can in fact do the quadratic formula, and if you do the quadratic formula, you will get this for an r, which means that alpha is equal to -1/6, and beta is equal to 1. Here's my general formula for y, and then we can go ahead and find C1 and C2 using my initial conditions. What I would do first is find y prime, not forgetting to use the product rule, and then using the initial conditions I would find these following values for C1 and C2. And you should try to do this on your own to make sure you get these answers. And this would be my specific solution given my initial conditions. But actually I want to look at what this looks like in terms of a graph, so I'm going to use Desmos. And this is what it would look like. And this makes sense. If I have a spring that's bouncing and it's in, say, air, then eventually it's going to start slowing down. So I see this sinusoidal change, but it's being damped by an overall exponential function. So the real portion, the e to the negative x over 6, or t over 6, is what's dampening the sinusoidal portion of this. If there was absolutely no damping, there wouldn't be a real portion, and it would simply keep going on forever. So again, we've now gone over all three different types of solutions for second-order differential equations that are homogeneous. We have two real solutions, one repeated real, and two complex. These are always going to be the forms of the solutions when you encounter these types of problems.